we started with introduction. So we know that the heavy metal contamination, it is one of the major environmental problem that is facing today in the world. So our aim is to remove these heavy metals from the soil or from the water. So how this heavy metal get released into the environment? So that is the main part which we have to think about. So mainly it is due to the rapid industrialization. We know that urbanization and the calamities, many calamities, due to many calamities, these heavy metals get released into the environment. And we know that it creates a high risk to humans, plants, animals. We know all these things because even at a low concentration, very low concentration, we know that the presence of these heavy metals are toxic and even carcinogenic. So nowadays we know that many methods, conventional methods, are available to remove these heavy metals from either from the soil or from the water. But nowadays, these nanotechnology, it is getting attracted for this heavy metal removal. So some of the slides will be covering about the nanomaterials and the nanotechnology, and some of the slides will be covering the topic adsorption also. Okay, so the nanomaterials, why it's getting more attention for heavy metal adsorption? So it's having some advantages. What is that advantage? That is higher surface area, it is having high removal efficiency and also higher adsorption rate, faster adsorption rate. Because of that only, we introduce these nanomaterials for the heavy metal adsorption. Now, another term you can see here, it is polymer coated nanocomposite. Why polymer coated nanocomposite? That means we are coating this nanoparticle with some other material. So why this surface is modified? What happens? When the surface gets modified, what is the benefit? You can see here ion exchange property is increasing and also the adsorption property is getting high. So we coat this nanocomposite with either acid or any polymer or any graphene based or megamide. So in any way you can coat this nanoparticle to make it more effective in heavy metal removal. These are all general thing, but anyway, I am covering the slides. You can see the sources and impacts of heavy metals. As I already mentioned, that rapid industrialization. So you can see that types of industries which is releasing different types of heavy metals into the soil and in the water. So mainly electroplating industries, metal finishing industries, so many industries are there. And what all health issues are creating based on the presence of these heavy metals. That is also given here. You can see the carcinogenic diseases, liver damage. So we have to think about the removal of heavy metals from the soil and from the water. Now, below you can see the various methods available to remove the heavy metals like adsorption, precipitation, and exchange. So many methods are available now. Now, these are the standards of various heavy metals which to be noted, because when we dispose these effluent or when after the treatment, you have to look to the maximum contaminant level of each heavy metal. Then only we can say that the treatment is effective or not. Because you can see what all toxicities are created by each heavy metal. So these are the various heavy metals, and the maximum contaminant level means the maximum limit of this of each heavy metal which to be noted. Now these methods I've classified into three. You can see the three classifications done: physical method, chemical method, biological method. You all know that these are the three methods, and each method you can see the treatment techniques involved in it. In physical method, you can see sedimentation, screening, separation, etc. In the chemical methods also precipitation, ion exchange, adsorption. So many methods are there. In biological methods also we look into aerobic, anaerobic. So we know all these methods available not to remove the heavy metal removal. Now, when we look into these methods, why we concentrate only on one method, that is adsorption? Why, when we compare to the other methods, why we go behind adsorption technique? Because in many of the other techniques, the main disadvantage is that the sludge is getting more, or the amount of sludge formed after the treatment is more. So then after the treatment, then we have to think about how we have to manage the sludge, how we have to, where we will dispose the sludge, etc. We have to think about. So, but in case of adsorption, that amount of sludge, it is not a problem. Okay, so that is why more research studies are going behind the topic adsorption. Now, what is the advantages of adsorption? You can see here the simplicity in the operation, the low energy input, and the reuse potential of the adsorbent is high, safety in the operation also. And apart from the adsorption, as I told, the advantages, let me come to the nano-adsorbents. Why nano-adsorbent? You can see here, when we go to the size of the particle, if you are concentrating on a nanoscale particle, what is advantage? You can see the adsorption capacity is higher, large surface area. So what happens when the surface area increases, the adsorptive size also increases, so the higher adsorption capacity takes place. So here pore size distribution. So like that, more advantages are there in case of nano-adsorbents. Now, apart from this nano-adsorbent, again, as I mentioned in this previous slides, when we modify this nano-adsorbent with some chemicals or with some polymer or any other material, what happens then? Then here you can see the adsorption capacity again increases, the stability, it is getting high, large active sites are formed. So nowadays, most of the studies are going behind the surface modified nano-adsorbents because of the faster rate of removal. Now, this is a general one. You know what is adsorption. Now, here it is given. It is the separation process of transferring material from a liquid phase to the surface of a solid phase. Now, why I have shown this slide is, you can see here the adsorbate and the adsorbent. The adsorbate is getting adsorbed onto the surface of the solid. And another term you can see, desorption. Desorption is important because once we do the adsorption process and we are not thinking of the desorption, then again it creates a big environmental problem. So this desorption term, it is very important. So that's why I have shown this slide. Now you can see here various types of adsorbents used by various researchers. And in the removal of heavy metals, you can see the types of adsorbents. So in the type of adsorbents, there are both. That means the natural adsorbent is the, synthesized adsorbent is the, combination is the, okay, nanocomposites, surface modified. So different types of adsorbents are shown here. And the adsorbent which removes the heavy metal, you can see the metal ions removed and the percentage, how much percentage it is removed, the adsorption capacity is shown here. And the main part is the isotherm and the model, because we should know which model or which process mechanism has taken place in this adsorption process, because we know that in the previous slide, in this mechanism of adsorption process, you can see only one layer. It's a monolayer. This adsorbate, you can see it's only a single layer. But there is a chance of double layer also, multi-layer formation can also be taken place. So in our process, or if you are doing some research study or experimental study, we should know whether it is a monolayer adsorption or a multi-layer adsorption. Okay, or is there any other reason for the adsorption that has taken place? So for that, we have to go do the isotherm study. At the same time, we have to do the model study also. You all will be knowing what are the the adsorption kinetics models available to know which model suits well with the experimental data or the equilibrium data. So that is shown here. So each adsorbent, heavy metal, percentage removal, isotherm or model, it is shown here. It is continued. So many research studies are there based on this adsorbent, various types of adsorbent, removing various types of heavy metals. Now coming to nanotechnology, we'll see what is this nanotechnology and what is nanoparticle, etc. Okay, you know what is a nanoparticle? A solid material which is having 1, 2, or 3 dimensions less than 100 nanometers. At least one dimension, if it is less than 100 nanometer, we can call it as a nanoparticle. And what is the use of this nanoparticle? Okay, so when the particle is becoming nano-sized, the surface area of the sorbent or surface area of the nanoparticle is getting increased. How? Due to the production of large number of nuclei. So what happens when the surface area increases, more number of active sites are generated, so the rate of adsorption also increases. That's why we are preferring nanoparticle. Now, if you are patterning or if you are rearranging or patterning matter to the nanoscale, any particle, if you are rearranging it to the nanoscale, only the fundamental properties will be getting changed, but the chemical composition will not be getting changed. Now, another term, it is magnetic nanocomposite. What is the importance of taking or considering magnetic nanocomposite in the removal of heavy metals? You know what is a composite. I'm not explaining more about it because different two or more substances having different physical characteristics. But what is the advantage if you are considering a composite material? The properties you can see here: large surface area, the absence of internal diffusion resistance, that means internal movement will be getting blocked, the high surface area to volume ratio, and better adsorption capacity, selectivity, stability. So all these are there in the composite. Now, why we are involving this iron oxide or macamite or graphene oxide into along with this nanocomposite or any composite? If you are involving or if you are incorporating this iron oxide or graphene oxide or any other magnetic chemical compound with the composite which you have prepared, then the particle will be changing to magnetic nanocomposite. Why? Because we are going to remove the heavy metal. So if it is at a faster rate or if it is having some magnetic property, the rate of adsorption will be at a faster mode. So for that only we are doing or we are synthesizing a magnetic nanocomposite. We can see what are the, just for an example, I'm showing the iron oxide because iron oxide, that is the normal chemical compound which is, in all the studies which the researchers are taking. So it's having high surface area, it is having high magnetic property. So in all the combinations, if you are using this iron oxide into it, it will be having, that particle will be having a magnetic property. So it will be, second statement, you can see easy separation of adsorbents from the system takes place if it is having a magnetic property. And here it is highly efficient and cost effective nano-adsorbent also if you are using an oxide. Now I'm showing some of the nanomaterials here. Yeah, these are all general terms. Carbon nanotubes, you know it, polymeric nanoadsorbents, zeolite, metal-based nanoadsorbents. Also, various types of nanoadsorbents are available. So, for an example, I'm showing some of the nano particle which our students have prepared for the BTech student projects. Okay, so on the right-hand side, you can see one product named nano-sized vetiver root. Okay, this was a student project, and what they have done is. Hope you will be knowing what is vetiver. Vetiver means ramacham plant. Ramacham. So you know that it is a medicinal plant. So it's having some kind of potential. So what we do is that the vetiver root we took, and at a suitable temperature we dried it, we crushed it, made it into nano size. So that is shown in the picture. So this nano-sized vetiver root, that powder, it is used for the adsorption process, and we have done many experimental studies, and from that we got the conclusion that more than 90% removal of the heavy metal has taken place. So that is one example. On below of slide, you can see here this one, the first one, you can see alumina iron oxide nanocomposite. It is a composite only. Okay, so alumina iron oxide nanocomposite. This material, it is synthesized one using chemical precipitation method. The first one, it is a natural product. You know, it is a vetiver plant. Okay, so that is a natural product. Just we have made it to nano size. But in this case, you can see here, it is a powder formed using synthesis of using chemical precipitation method. Okay, so this combination we call it as alumina iron oxide nanocomposite. And on the right hand side, you can see this powder coated with one polymer. Okay, so which polymer we have selected for coating? So based on the literature review or based on some journals, we took polypyrrole, pyrrole monomer for coating this alumina iron oxide nanocomposite because it is having so many advantages when you take a polymer. So we coated this alumina iron oxide nanocomposite with a polymer. Okay, and we have done the experimental studies with both the powders. Okay, and we found that more percentage removal has taken place when we coated this alumina iron oxide with pyrrole monomer. So this composite, we call it as a polypyrrole alumina iron oxide nanocomposite. Okay, so this is the way how we prepare or how we produce the nano material. Okay, either synthesis, either in the natural one, from the natural one, or synthesis product also can be made. This is the main part of the presentation. You can see here characterization of nanocomposite, because we know that why we do characterization. Characterization, it is mainly done to find out the surface morphology of the particle, the characteristic of the particle, what all elements are present in the particle, the nature of the functional groups present, okay, then the stability of the particle. So many things can be found by using these kind of analysis. Okay, we'll see one by one. SEM analysis, you can see surface characteristic of particles can be found. TEM analysis, it is morphologic characteristics. XRD, phase identification of a crystalline material. EDX, it is elemental analysis, that means elements, what all elements are present. FTIR, it is the functional group or the chemical bond that is there in the particle can be found at various wavelengths. TGA means thermogravimetric analysis. Thermogravimetric analysis. I have not given the full form. I know that you all are familiar with the terms because I've heard about few sessions I've heard, and I've heard BET analysis in Shivanandan Acharya sir class. So same these terms might be will be a repetition for all of you. So TGA means thermogravimetric analysis. BET analysis, you have heard it, to find the area and volume of the particles. Now, with example only, I am going to present. Now, you can see here what is SEM analysis. We know to obtain the information about the surface topography and composition. Now, here I've shown the two pictorial images of the nanocomposite which I have prepared before adsorption and after adsorption. Okay, so the before adsorption, two magnification, it is given like 50 micrometer, you can see here, and this is 5 micrometer. So again, microscopic level is getting in a smaller level, it is visible here. Same way after adsorption also, this is 50 micrometer and this is 5 micrometer. So before adsorption, you can see the nanocomposite structure, and below that, this is after adsorption. Okay, some changes have taken place. After adsorption means the metal ions getting adsorbed onto this nanoparticle. So some structural changes or some changes it is observed in this picture, but more clearly you can see in this 5 micrometer magnification. Here you can see the before adsorption image, but in this slide it is clearly visible that the metal ion, whether it is copper, chromium, lead, whatever it may be, after the adsorption process, the adsorption of or the metal ions have adsorbed onto the binding sites. Okay, you can see here. So this is this is the interpretation of SEM analysis. And in some cases, this kind of adsorption will not be visible, but more, if not, no problem. But from the SEM analysis, you can find out whether the particle, if it is a spherical nature particle, fibrous nature particle, or rectangular shape particle. So those data also can be obtained from this SEM analysis. But in our study, you can see it is clearly visible. This is one identification. Even though after completing an experimental study, we are saying that our particle is more effective in the complete removal of metal ions. This is the pictorial record. This is the main proof we can show that here the adsorption can take place. Okay. Now coming to the TEM analysis. TEM analysis is mainly morphological and crystallographic information of the sample. And when we done TEM analysis of, you can see different magnification of 20 nanometer, 50, 100 nanometer, it is done here. In all these pictures, it is clearly visible that the particles are spherically shaped particles. And it is together, it is in a cluster form. You can see here, agglomeration of particles. All particles are stick together. So that type of particles, we call it as, here you can see, we call it as nanoclusters. Okay, nanoclusters. So normally when nanoclusters are formed, it is said that then the size of the particle will be mostly in 0 to 2 nanometer scale. Then only this cluster formation takes place. But there is an advantage, even though if nanoclusters are formed, the high adsorption capacity will be increased. So this is TEM analysis to know the morphological characteristics. Another important one, it is XRD analysis. You will be knowing this, but an example only I am explaining to make it clear. XRD means X-ray diffraction analysis. So when you get a nanoparticle, how will you identify whether it is a nanoparticle or not? So the first analysis which we are doing, it is XRD analysis, because this XRD analysis, it is done to find the crystallographic information. You'll be getting the crystallite sizes from this graph, and also the phase identification also will be obtained. Now from this graph, you can see so many peaks are developed. In this graph, you can see so many peaks are there. And in these peaks, you can see so many diffraction angles are written here. Okay, so that diffraction angles, we call it as theta. Okay, 2 theta, we call it as. Now, this equation is known as Scherer equation. Scherer equation. You'll be knowing that the Scherer equation, you can see the equation L is equal to 0.9 lambda by beta cos theta. What is beta? This full width at maximum level. You can see the peak, and here you'll be having some width. Okay, so that width is taken at half maximum. Okay, so that is beta. Theta means the diffraction angle. It will be obtained from this graph. So substituting all these values, you can see the L, the crystallized sizes obtained for each peak. You can see here. What is the size of these crystallized sizes? You can see it is ranging from 13 to 24 nanometer sizes. What does it mean? Huh? So we cannot call these, since all the values are between 13 to 24 nanometer, we cannot say that this is, this is the particle size. We cannot call it as a particle size, because when we compare with particle size and crystalline size, it is smaller than the particle size. Okay, so if you are obtaining this crystalline size as 13 to 24 nanometer, we can say that the particle belongs to a nanoparticle group. Okay, because all these peaks form having the crystallized sizes of this nanometer only, and we know that if it is less than 100 nanometer, we call that particle as a nanoparticle. Okay, so that is one identification. Then another thing from the XRD analysis is phase identification. Now here you can see so many phases. It is written in the first column. That is based on these values, 2 theta, based on these values, the different phases are written here. And from these phases, you can identify which structure is formed, whether rhombohedral structure, okay, orthorhombic structure. So different structures are the amorphous structure. So different structures are there. So based on these phases only, we can find out the structure. Okay. Now, how you can identify these phases? There is one standard named Joint Committee on Powder Diffraction Standard. Like IS code, we have a standard JCPDS, Joint Committee on Powder Diffraction Standard. So by referring that JCPDS database, you will be getting which phase it belongs. You can see here the first 3 readings belong to iron oxide phase, which is having a rhombohedral structure. And this value 24.285, based on that data, JCPDS data, it shows that it resembles polypyrrole with amorphous properties. That means disordered structure. Okay. Then another one you can see aluminum hydroxide phase. Okay. So these are the different, which is having orthorhombic structure, aluminum hydroxide phase. So the phase identification and the structure, the crystalline structure and the crystallite sizes can be identified from this XRD analysis. Coming to EDX analysis, why we do the EDX analysis before adsorption and after adsorption? As I said before, all these are important if you are going behind an adsorption process, because only with the values we cannot claim that the adsorption has taken place. But with the pictorial representation or with the graphical representation, we can prove that the adsorption has taken place. So what is EDX analysis? It is mainly to find out which all elements are present in the nanocomposite. You can see here, just to compare, I've taken one example. So this is the EDX analysis done for a nanocomposite or nano-adsorbent before adsorption. And this is the EDX analysis done after adsorption. Now, before adsorption, you can see there is no copper find. You can see here, no copper, but you can see many other elements present in the composite. And this table represents the how much percentage of each element are there in the particle, nanoparticle. And after adsorption, you can see here the copper presence is there. So what does it indicate? The adsorption has taken place. Before, the copper presence was not there, but after adsorption process, after the experimental studies, we found that copper element is there in the nanoparticle now. So it is an indication of the adsorption. The heavy metal is adsorbed onto the surface of the nanoparticle. That for that purpose only we do this EDX analysis. Next, another important one analysis, it is FTIR, that means Fourier transform infrared analysis. This is mainly used to determine the nature of the functional group, associated functional group, and interaction of IR radiation with matter. And also it reflects the optical properties of nanoparticle. Now, mainly this analysis is done to find the chemical bond through the IR bond of a chemical bond of a molecule through IR spectrum. So this is mainly done to find out whether the particle which we are claiming, that we are saying, for an example, I've shown one powder like polypyrrole alumina oxide nanocomposite. We are claiming that the product which we are prepared, which I have prepared, it is a polypyrrole alumina oxide nanocomposite. But where is the proof? Can we call any product it as alumina oxide nanocomposite? No. So by this FTIR analysis, you have to check whether we can call that powder or the product formed, whether it is a polypyrrole alumina oxide nanocomposite. So whatever product we are forming, there are some bands. The chemical bonds are there in each particle. So with respect to the IR spectrum we can refer in the Google also. So IR spectra, with reference to IR spectra, you have to find out whether all the bands corresponding to this polypyrrole alumina oxide nanocomposite are present in this analysis. So the first one you can see before adsorption, I've done the FTIR analysis of the nanocomposite, and now I am going to check whether the product which I have prepared, whether it belongs to polypyrrole or alumina or iron oxide, can we call it as this nanocomposite? So for that, FTIR analysis is done, and I've checked all the bands formed here. You can see so many bends, peaks, etc. Okay, so these are the bands formed, and these values are taken with the IR spectra. You have to check it, cross-check it. Here you can see the wavelength. So based on the wavelength, if polypyrrole is present, certain bands should be there. Okay. If alumina iron oxide, the certain bands like carbon-carbon single bond, carbon-carbon double bond, CH bond, iron oxide, like that. So many bands, so many chemical bonds should be present. Okay. So those to be checked. Then only we can conclude that it is a polypyrrole composite. Now, after that, we are doing the experimental study, and after conducting the experimental study, again we have to go for FTIR analysis. After the adsorption, the same nanocomposite is taken for the analysis. And here what has happened? Just compare the two graphs. You can see some changes have been occurred in the graphs. Okay, so just see the first graph. You can see so many bends and peaks here, but in the second graph, there is a shift has taken place. Either the first reading gone up, or the second reading you can see so many peaks here, or else it is going down. So many shift has taken place. Okay. So for an example, let me how we will interpret from these analysis before adsorption and after adsorption. You can see the value. Let me take one value. I don't know whether the value is clear, but I will read the value. It is like 1567. Okay, 1567, 1567. This side, if I am taking, it's 1543. Okay, see the band also. This is this 1567. It is in between 1500 to 2000 range. Here also 1500 to 2000 range. The value it is 1543. What has happened to that shift? 1567 changed to 1543. That means reduced. What is the indication? Whether adsorption has taken place and what type of adsorption it is. Okay. Now there are two types of adsorption. You know that: physical adsorption and chemical adsorption. Physical adsorption means just physically. That means the adsorbate is getting adhered to it is getting attracted to the surface of the adsorbent. That is physical adsorption. But chemical adsorption means between the adsorbent and the adsorbate, so many reactions is taking place, and then the metal ions is getting adsorbed to the binding site. So here what has happened? The value got decreased. It is not increased. Here there are two chances. The value of 1567 can be increased to 1600 or can be decreased to 1543. Two chances can occur. The indication is if it is increased to 1600, then that means it is physical adsorption. That means that band 1567, if it is physically adsorbed, value will be increasing. But in the other case, it is chemical adsorption. That is why it got decreased. So here also we can conclude that the adsorption has taken place because so many shift you can see. So like that, if you take each value and compare with before adsorption and after adsorption, you can finally conclude with so many findings. Coming to TG analysis. This TG thermogravimetric analysis is very important because when we prepare a product, a nanoparticle or nanocomposite, whatever product we are preparing, we have to check the stability of that product, because you know that we are dealing with the temperature, varying temperatures. So how long this material is having the stability. Now you can see the example, the graphical representation here for the TG analysis. Started with 41 degree temperature till 861 degree temperature. So in the beginning, you can see the rapid weight loss. You can see rapid weight loss in the beginning. It is mainly due to the loss of moisture. But then a gradual degradation has taken place when the temperature started from 100 to 450. Okay, then from 450, you can see it is almost stable. Okay, so this is the changes that is happening to the material. But further adsorption and this TG analysis, that part I have not taken into account. That I think studies are there. We have to refer various journals to go behind this TG analysis and the temperature study. Now, this part I'm not explaining more because Acharya sir have taken a lot about this wet analysis. This is mainly done to find the surface area and pore volume of the particle. And from this, we will not be getting the particle size, but the pore size will be obtained. And so many other data like surface area, pore volume, you can see here. All these data will be obtained if you are doing this wet analysis. This is also, in the previous session it is explained, and the isotherm plots. So in this plot, you can see here the 50, less than 50 pore diameter, more grain crystals are formed here. Then below slide, you can see the adsorption and desorption plot. In the beginning, it was flat due to the adsorption, but later on, when the pressure increased, it got separated, and then due to agglomeration of the particles, it has formed a lag loop. So this is these all informations will be obtained by the wet analysis. Now, little about the adsorption process. Okay, this batch mode adsorption studies is the important one, experimental study which we are doing in the adsorption process. These are the main parameters which we have to think about when we do the adsorption. You know that pH is an important factor because it affects the degree of ionization and the surface charge of the adsorbent. And you know what will happen when the pH decreases. Normally, in most of the studies, you can see that when the pH decreases, what happens? The binding site gets protonated. Protonated means positively charged. Okay, positively charged. So only the negative metal ions get attracted to this positively charged binding site. But in case of metal ions, when the pH increases, what happens? It gets deprotonated. So the binding site gets negatively charged. So these kind of changes takes place in pH variations. So the effect of pH to be studied in the adsorption process. Next is effect of contact time. So why we think about the contact time? Because for the economical purpose, and also the equilibrium time is important to know at what time the maximum removal has taken place, because or else the study will be will be extending for a longer time. So we have to think about the optimum time, the equilibrium time, where the maximum removal has taken place. Another parameter, it is adsorbent dosage. Just imagine we are putting so many adsorbent into the soil or water to remove the contaminants or to remove the metal ions. What happens is, more than removal of heavy metals, it may contaminate the soil or the water if the adsorbent dosage increases. So there also we have to find out what should be the maximum limit of it or the optimum adsorbent dosage for the maximum removal of metal ions. Then initial concentration, we know that lesser concentration of solution, lesser concentration of metal ions, more amount of the adsorption takes place in the binding site. If the concentration increases, slowly the clogging takes place at a faster rate. Okay, then temperature. Temperature, it is very important. As I said, the adsorbent nature will have a tendency for the elongation or something like that. Okay, so that temperature part is very important. What is happening when the temperature is increasing and when the temperature is decreasing, that also to be taken into account. And based on that, thermodynamic studies also to be done to find the feasibility of the process. This is very general. You know how the percentage removal to be calculated in the adsorption studies, and also the adsorption capacity, the formula, you know it. I'm not going in detail. And coming to the isotherm, in adsorption studies, the important two topics are adsorption isotherm and adsorption kinetics. Why isotherms are important? Because it gives information on the nature of solute surface interaction at a constant temperature. So we should study how these adsorption has taken place, what is the mechanism behind it, etc. So that relationship between the metal ion concentration and the quantity of metal ions adsorbed. So all these details will be obtained when you go for this adsorption isotherm study. Kinetics also, you can see here, the controlling mechanism of adsorption is obtained using this from this adsorption kinetic study. I'm giving only the types of isotherms and types of models. Okay, you can see here different isotherms are available. I've shown only 3 here. Okay, different isotherms are the Langmuir isotherm. I've shown here in bracket what is happening in Langmuir isotherm. It is monolayer adsorption. Then Freundlich isotherm, what is happening there? Multi-layer adsorption is taking place. Temkin isotherm, it relates with the heat of adsorption. So based on all the experimental data which we have obtained through the studies, from that, with respect to that data, we have to do all the calculation with these equations, these isotherm equations, and find out which isotherm suits well with the experimental data. So that isotherm fits well in our adsorption process. That is a technique. Another isotherm is the Dubinin isotherm. So many isotherms are there. Okay, that you have to refer the journals, etc. You can see here the kinetic study which we have done. Okay, the 4 models like pseudo first order model, second order model, Elovich model, intraparticle diffusion model, like that different models are there. Now what is happening to pseudo first order model? This in pseudo first order model, the adsorption is taking place only to one active site. So many active sites, so many binding sites will be available in the particle when you consider the nanocomposite. So whether it is happening only to one active site, that is pseudo first order model. Second order model, you can see that the physico-chemical adsorption, both the adsorption is taking place. So that 2 active sites will be getting filled with this metal ions. So like that, so many mechanism is happening. The third one you can see here, Elovich model. What is Elovich model? The chemisorption kinetic is taking place. Intraparticle diffusion model means it consists of 3 types. 3 diffusions are happening. One is film diffusion, second pore diffusion, and the third one intraparticle transport. So 3 diffusion diffusions are happening in intraparticle diffusion model. So these models, you can see so many equations are there corresponding to each model based on the data which we obtained from the experimental study. Using this equation, find out all the parameters and find all the parameters and check whether the value or the equilibrium data fits with which model or the mechanism. What is the mechanism behind the adsorption taken place in our study? So that should be checked using this adsorption kinetics. And if it is pseudo second order model, we can conclude that both the adsorption, physical and chemical adsorption, has taken place in our study, in our adsorption study. That should be the conclusion. Now, another important study, it is thermodynamic study. So this is also an important factor in adsorption study because it relates with three parameters. You can see here: Gibbs free energy change, entropy change, and enthalpy change. Now, what the formula, it is also given, the equation it is given here to find out the Gibbs free energy change, and energy of activation is also another important factor to be considered in the adsorption process. Now, after doing all these calculations, you can check the delta G degree value. If it is less than zero, that means if the value, if it is negative value, we can see that the nature of the reaction is spontaneous. Okay, and delta H degree, that means the enthalpy change. Okay, delta H degree value, if it is positive, greater than zero, we can say that the reaction is endothermic reaction. Two types of reaction, it can happen, endothermic or exothermic. But in our study, means if the value of it is greater than zero, it can be endothermic reaction. Okay, and delta S degree, that means the entropy change. If it is positive value or greater than zero, what happens? As the reaction proceeds, the randomness increases. Okay. For an example, I've shown this picture, this graph and table. So in this graph, you can see the temperature delta G with temperature drawn. And here in the table also, you can see with respect to each temperature, you can see the delta G degree value, enthalpy change, entropy change, and energy of activation. So here, as we mentioned in the previous slide, if delta G degree is less than zero, that means negative value. Here, all the delta G degree values are negative. So what is the indication? Spontaneous reaction is very fast. Spontaneous reaction has taken place. And delta H degree, it is positive value. So what does it indicate? It is endothermic reaction has taken place. Then EA, here, delta S also, it is there. It is positive value. So randomness increases as the reaction proceeds. And this energy of activation, the value, it is 8 point something in all the temperature. So normally it is said that 5 to 50 kilojoule per mole, the energy of activation, if it is in range between 5 to 50, we say that the physical adsorption process has taken place. But in case of 50 to 600 or whatever, that range, we say that the adsorption is um, chemical adsorption process. So that is the value, means based on the range only we can conclude whether the adsorption is physical or chemical adsorption. Now the last one, it is very important, as I said in the beginning, desorption studies. How we will do the desorption studies? Now, we normally always will be thinking about the adsorption process, how much efficiency obtained, how much faster it is, what is the time taken, dosage, etc., temperature, etc. But this is very important because, or else, as I said, after doing all these adsorption process, this nano-adsorbent is taken. Okay, nano-adsorbent is taken. This adsorbent will be having so many metal ions which got adsorbed. What you will do with this adsorbent? So if you are throwing it to the environment, what happens? Again, it gets contaminated. Okay, so there is no, yeah. Then in doing this adsorption process, the all the idea will be getting useless if you are just again throwing back to the environment, because we are doing all these things to clean the environment only. Okay, so we have to think about this desorption studies. So what is a potential adsorbent? When you select an adsorbent, you have to think about both the qualities. Which all qualities? It is both the qualities like adsorption and desorption of heavy metal ions. So both the factors are important, adsorption and desorption. How you will do desorption? Okay, so this desorption of metal ions, it is mainly happening in the adsorbent fresh cycle. The beginning one you can see here. The first one is the adsorbent which we have prepared. Okay, and in this fresh adsorbent, what is the removal efficiency? Almost 100% removal efficiency obtained. Okay, so after completing the adsorption process, what you will do? That adsorbent is taken with this from this any acid that you have to check which acid is suited for the for the adsorbent which we have prepared. So if you are putting the adsorbent into that acid solution, the metal ions which gets which will be eluted from this adsorbent, okay, can be removed from this adsorbent. So in the first stage, in the first cycle, you can see this was 100%, and in the second you can see around 98% desorption efficiency has taken place. That means after desorption, this adsorbent can be reused again. Okay, so or else just imagine we have to collect so many adsorbent for this process. That is practically not possible. So with one adsorbent, at least you have to do 3 or 5 cycles. You have to see the efficiency. Okay, then go for the fresh adsorbent again. So again, after the fresh piece, you can see desorption efficiency obtained. That same adsorbent is used for the next cycle, that is the first cycle. Do the adsorption process. After completing the adsorption, go for the desorption, like that second cycle, third cycle. So finally, the third cycle, you can see around 75% desorption efficiency. It's only the rest of the percentage. And that means that adsorbent is filled with the metal ions. It is not getting removed. So around 5 or 6 cycles you can do, and you can find the desorption efficiency. After that, you have to think about a new adsorbent. Okay. Coming to the conclusion. So in this presentation, I've included the use of nanocomposites in the removal of heavy metals from wastewater. And I've explained about the characterization of nanoparticles before and after adsorption, and also how to interpret the results from the graphical representation or the pictorial representation. And we have gone through some of the terms like adsorption, isotherms, and kinetic study to determine the best model that suits well with equilibrium data, and also regarding the desorption studies like elution of metal ions from the nanocomposite after adsorption, so that regeneration and reuse of the nanocomposite is done. Okay, so that's all about the presentation. So